Wow, we are really getting to know Dan pretty well in this class. Anybody who says that online classes are impersonal has clearly never taken this class, right? Okay, so I know most of you probably have an opinion about this over-under situation with the toilet paper. I completely agree with Dan that over is the only way to go. I don't go into other people's bathrooms and change it. Okay, so we are going to engage that question that Dan asked. Is there a gender difference between men and women, obviously, in how they like to put their toilet paper? Do they like to have it over or under? So we went and asked a bunch of men and women, a bunch of people, about their preference. So I want to show you the data, and then you can look and see if you can tell. What's your guess? What do you think? Are women more likely to say over, or are they more likely to say under? What about men? Under or over? Okay. We don't really have to guess. We're going to work this out in a problem in a minute. But speaking of guesses, speaking about making a prediction, let's go ahead and write our hypotheses, just like we discussed in the last unit. For every unit from here on out, we're going to write hypotheses at the beginning of our problems to lay out what we expect to find, right? We always expect to find a significant difference. That's the research hypothesis. It says we expect to find a significant relationship between variables, and our null hypothesis says we don't expect to find a significant relationship between variables. So go ahead, take a pause, write out your hypotheses or think them through in your head. Once you're done, hit play, come back, and we'll compare what you have with what I have, and we'll see how they compare. Okay, do you have them written? Let's see what I have. So I'm saying the null hypothesis is there is not a significant relationship between gender and toilet paper placement. Yours might not sound exactly like this. We don't ever have to match our words exactly, but you should have something in there about there being no relationship between our variables. And then our research hypothesis says, yes, there is a relationship between gender and toilet paper placement. You may have said women are more likely to prefer over to men, something like that. But in either way, we want to say that there is a relationship. The gender that you are influences how you like to hang your toilet paper on the rack. Okay, so how are we going to solve this? You might have guessed already that because we're in the chi-square topic, we're going to use chi-square, and you're right. But you don't have to guess. You can think about how we're measuring these variables, right? Toilet paper placement, either over or under, is a nominal variable. Same thing with gender, male or female. And so you'll recall that if we have a nominal level independent variable and a nominal level dependent variable, then we're going to use chi-square. That's the formula you see here. All right, so the formula looks a little daunting, but if you remember back to Dan's Lightboard lecture, it's not so hard. We're just going to take the sum of a series of numbers and divide by n. So that series of numbers is what we have to calculate. So looking at the top of this fraction, we see that we need to take the FO, that's the observed frequency, the number that we actually found when we talked to these people about their toilet paper preferences. We're going to subtract the FE, the expected frequency. And this is a number that we're going to calculate. So we'll think about how to calculate that in just a minute, but once we have that data, we'll just do one number minus the other, square that, and then divide by the expected number again. This is giving us a ratio. We'll do that for each cell in our table. We'll talk about that a little bit more in a minute. Sum it up, and that's our chi-square. In theory, it's a pretty simple exercise. You just have to know what to plug in where, which is the tricky part about this. Okay, so let's talk about this expected frequency formula. We're going to take the row total times the column total for the cell that we're interested in. So we're going to set up a table. We're going to look at a particular cell, and for that cell, there's a row total and a column total. There are numbers in each of those cells. We'll just multiply them, divide by the number in the entire set, in the entire data set, and that's our FE for a particular cell. Okay, so, and then the last thing we need to talk about at the end of our problem is degrees of freedom. So we'll just know that we have a formula for that, and we'll come back to that at the end. All right, so let's put this together. Let's look at the data in a table. That's going to give us a better idea about what we're talking about. So first, we have to move from that long data list that we started with to this kind of table. This summarizes everything for us. So if we went back to that first table, we would see that we have 12 women and 10 men. That's what we have here reflected in the bottom row, the 12 and the 10. And then if we went back and counted up the overs, not regardless of the gender, we see that we have 14 people who said over and 8 people who said under. And that gives us a total of 22 people. So either way you add that up across the bottom, down the right-hand side, you're getting 22. Okay, so those are the total row and column. We're going to use those in a minute again. But what we want to talk about now is how to fill in the inside of the table. The kind of table we have here is set up as a 2 by 2 table. You're going to hear us talk about the size and the dimensions of a table a lot. And this one is a 2 by 2, and that's because we have each of our variables can only be measured or can only have a response in one of 2 ways. So on gender, you can either be a woman or a man. For your toilet paper placement, you can either like it over or under. So because there are 2 responses on each variable, we're going to have a 2 by 2 table. All right, now that we have our observed values table set up, this is just a summary of our actual data. We're going to transition this over to our expected values table so that we can see what our data set would look like if there was no relationship between gender and toilet paper placement. That's what our expected values table tells us. This is the expected value given no relationship. This sort of represents the null hypothesis, right? Okay, so the first thing we'll do when we set up an expected values table is fill in the row titles, men, women, total. We'll set up the column titles, over, under, and total, and then we'll fill in those totals. So 14 overs, 8 unders, 12 women, 10 men, 22 total. We have the exact same characteristics as our real data, right? We still have 12 women and 10 men, but the numbers inside of the table are going to represent what our data would look like if men were no more likely to choose over than women were, and women are no more likely to choose under than men are. Okay, so that we get to these numbers using the FE formula, the expected frequency formula that I showed you on the previous page. So I've already worked these out for us so that you can kind of follow along with me and see how I'm doing this. Follow my logic. So we're going to start with this first one in the upper left, the FE, the expected frequency for WO, and that's shortcut for women over. So in the 4x4 table, inside of the expected values table, you see women over, right? That top cell, top left cell is what we're working on here. So the row total for that cell is 14. Just go across till you get to the total and you see 14. Go down the column until you get to the total and you see 12. And then divide that 14 times 12 by 22, which is the total number in the data set. That's how I filled in my formula. Do the math, you get 7.6. Pop that into your table in that cell that we were just working on. Let's go over 1 to men over, right? That's the also in the top row of that 2 by 2 table within the expected values table. So we go over, we're going to have the same row total, of course, because we're in the same row. That's 14. We're going to have a different column total now because we're in a different column. That's 10. Then we're going to divide again by 22 because we have the same number of data cases all throughout this problem. So 14 times 10 divided by 22 gives us 6.4. I think you see where we're going with this. So when we do the expected frequency for women under in the next row, we're going to do 8 times 12 divided by 22, and that'll give us 4.4. And then finally 8 times 10 for men under divided by 22 gives us 3.6. Now we just transfer all of those numbers into the table, and here's what we have. This is when we're finally ready to calculate chi-square, because we have our 2 data sets. We have what we actually have in the observed values table, and then we have what we would have if the null hypothesis were true in the expected values table. So this bottom table down here is going to give us the calculated chi-square, right? So it's a pretty easy table to set up. You simply transfer your observed values into the first column. Then you put in your expected values in the second column. In the third column, we need to just subtract the second column from the third. So 10 minus 7.6 gives us 2.4 in that first row. Do it again in the second row. 4 minus 6.4 gives us negative 2.4. Keep going down, and you can see we get negative 2.4 again and then positive 2.4 again. Now, when you first start doing this, you'll think, I must be doing something wrong. Why are all these numbers the same? Well, I'll tell you, every time you do this type of problem with a 2 by 2 table, just the way it works out, just the characteristics of the table, you're always going to get the same value. 2 will be positive, 2 will be negative. It just is like that. So it's actually really helpful so that if you are working on a 2 by 2 table and you don't get the same value, go back and see where you've done something wrong. You probably just carried your values over from a table wrong, something like that. Okay, in the next column, Simple. We're just going to square each of those values, and because they're all the same absolute value, or because a negative times a negative or a negative squared is a positive value, all of the values in this fourth column are going to be the same. 2.4 squared is 5.6. Now in the last column, we'll take that 5.76 and we'll divide by the green number or the number in the expected column. And this gives us sort of a ratio of the difference by what we would have expected. Okay, so pretty easy math again. 5.76 divided by, in the first row, 7.6 gives us 0.76. Second row, 5.76 divided by 6.4 gives us 0.90, and so on down the column. Then we have all four of our rows filled in the last column, and the final step is just to sum those. Sum 0.76 plus 0.9 plus 1.31 plus 1.6, right? That gives us 4.57. And guess what? That's it. We have come up with our calculated chi-square value. Great. It was time consuming. There were a lot of steps, but we did it. It wasn't so hard. I think you could definitely do this on your own. But wait, we did it. We have 4.57 for our chi-square value. What does it mean? What have we determined? What does that mean about men and women and their toilet paper preference? Well, right now we don't know. We have one more step. Every time we do this from here on out, we're going to calculate a value. It could be chi-square, the t-test, ANOVA, whatever. We're going to have a calculated value, and then we're going to compare it with a critical value. And that critical value is always going to come from a table. And every single time, if our calculated value is higher than our critical value, if it's higher, then we'll say that yes, we found a significant relationship. But if our calculated value is lower than our critical value, then we'll say no, there is no significant relationship. That's just how all of these problems work. Once you do a few of them, it just becomes sort of intuitive about what you're doing. You'll get a low number, you'll say, oh, no way, is that going to be higher than that critical value? I bet there's going to be no significant difference. All right, in order to look at the chi-square table and get the critical value that we need for this problem, we need two things. First, we need the significance level. For any problem, the significance level is going to be the probability that we're incorrectly rejecting the HO. And I won't go into this in very much detail because we discussed it previously, but basically we want that value to be very low. And for every problem in this course, we're going to use 0.05. That means we have about a 5% chance of getting this wrong. Okay, so every time I say you need the significance value, you know to use 0.05. And in every table, there's going to be a column for 0.05. The second thing we're going to need is the degrees of freedom. So for every chi-square table, there is a specific degrees of freedom, and it's a fairly easy thing to calculate. So the formula for degrees of freedom is simply the number of rows in our table minus the number of columns in our table. So we're not talking about the entire table that has the column headings and the row totals and all of that. We just need the middle of the table, that one that where we keep putting in values. So we have a 2 by 2 table. That's where all the meat of the table is. So if we have a 2 by 2 table, that means we have 2 rows, 2 columns, right? And so that means if R is the number of rows in our degrees of freedom formula, then we're going to say 2 minus 1 is the first part of that formula, and we have 2 columns. So C here is 2. So we're going to say 2 minus 1 times 2 minus 1. That gives us 1 times 1, and that's 1. Degrees of freedom for a 2 by 2 table is 1. Every single time you have a 2 by 2 table, your degrees of freedom is going to be 1. Okay, so we know that our significance level is 0.05, and our degrees of freedom is 1. So let's look at the chi-square table and see how we can use those two pieces of information to find the critical chi-square value that we need. So along the top, we have these different numbers. You need to find the 0.05 column. And then along the side, we have various degrees of freedom. And so we're going to use 1. For all of the tables that we're going to use in this class, we're going to have a very small degree of freedom. To get a large degree of freedom, you'd have to have an enormous table, and it would be just unwieldy to calculate. So we're going to keep it small. So we'll always be looking towards the top of the table. In this case, we're using the 0.05 column, which is the second column. We're using degrees of freedom as 1. We'll just see where they intersect. And here we see in the table that where they intersect, we get the critical value that we need. That's 3.841. That's the value that we need to compare with our calculated value. So what does this mean? So now we have two values. What can we now determine about our problem that we started with this relationship between gender and toilet paper placement based on these two values. So I told you before that if your calculated value is higher than your critical value, then you have found a significant relationship. Again, if your calculated value is lower than your critical value, then you can conclude no significant relationship. So obviously in our example, 4.57 is greater than 3.841, so we have found a significant relationship. So let's bring this full circle. Let's go right back to the hypotheses. What does this mean? We have to make a decision about our hypotheses. We're either going to reject the null hypothesis and say, no, null hypothesis, you think there's not going to be a significant relationship, but oh yes, there is. Or we can say, oh, null hypothesis, you were right. There is no relationship between our variables. In this case, because we have just found, with the calculated chi-square value being higher than the critical chi-square value, that there is a relationship between these two variables, we get to reject the null hypothesis. That's generally what we want to do when we do these research projects. We want to say, haha, null hypothesis, you're wrong. And the research hypothesis that says, yes, there is a relationship between the two variables is the conclusion that we'll come to. So we can go back to Dan and say, guess what? You were right. There is a gender difference. Perhaps women are more likely, I think that's what the data showed, and women are more likely to choose over, and men are more likely to choose under. So what we're hoping that you got from this example is, number one, how to calculate the chi-square formula. It looks pretty awful when you look at all the stuff you have to do, all the little calculations. But once you do it a few times, I think you'll see that it's just a bunch of easy steps. And if you can just power through all those steps, it's a really easy and I think kind of fun thing to calculate. Okay, number two, in the bigger picture, what we've just done is your first hypothesis test, right? A chi-square test is one way to test a hypothesis. We're going to move on to t-table or t-test, ANOVA test, regression, correlation. These are all ways to test hypotheses. And when we do hypothesis tests, we always do them in the same order. We're going to start by writing out our hypotheses. That's the first step, and that's what we did here. Next, we will choose a test. And how do you choose a test? You do it based on your level of measurement. So in this case, we had two nominal variables, so we chose chi-square. We'll have a different level of measurement in the next unit, and that'll result in a different test. And then we'll calculate in this case, the chi-square, or in any other example, we'll calculate the test statistic. We'll compare our calculated value to a critical value, which we'll look up in a table, and then we'll come full circle again and decide what that means about our hypothesis. We'll either reject the null or fail to reject the null. So as you work through the problems for this unit, be thinking not only about how to get to the end of the problem and calculate the chi-square value, but what does it mean, and also what does it mean in the big picture? What have you learned? But also think through this hypothesis testing process. Become familiar with it because you're about to do it a lot more times in the next coming weeks.